Swayam Prabha. Digital India. Educated India.
So essentially, if we are looking into the fraction which is between 0 and 1, if I draw a line, we are dividing the whole section into 3 parts, where this fraction or this side is equal to this side, and this is another side. In this case, it is also clear from this image is that this distance is going to be equal to this distance. Now, if we eliminate one of the portion which is equal, either this side or this side, then we will be left with this portion or this portion. Let us take the portion this is eliminated. Then we are left with this portion. We have already 1 point here, and once we look into this point in the next level, which is, we are saying the 3 by 8 and 2 by 8, which is of this level, because we are eliminating one of them, this one if we are eliminating, then the 3 by 8 is also going to represent another 2 by 8 and 1 by 8, which means I can say the 3 by 8, if this is my 3 by 8, it is going to represent another 2 by 8, means some portion which is going to be same as this portion, which was the earlier portion which we had considered. And if we again eliminate, we will keep on getting 1 point again and again, which can be used. So let's look into in a better way in a general format. In this case, as we are saying, we have the lower bound and the upper bound, which is A and B. Then if we are looking into the interval, which is the total distance between A and B, this part, and then we are looking into the 2 Fibonacci number ratio to represent a point within this search space, which we are calling it as L21 in the first iteration and L11 in the first iteration. So L2 is going to be this region and L1 is going to be this region. So the L2 is either going to be this or this. Now once we eliminate one of the smaller region, in this case we can say L1. So if we eliminate this region, then we are left with the L2 region, which is becoming the new region, means my boundary is moved to this point, and in this point we are seeing that the distance is exactly the same with L21 of the previous iteration, which can be represented as the following two numbers of that number, which is n-2 and n-3, with respect to the initial region. And then in here, if we are further dividing the two regions, we can say the L22 in the second iteration is going to be one component of this, which is here, and the other one is going to be this component, which is here. Now this one can be reasonably written with respect to the new boundary condition as well, and L12 can be written with respect to the new boundary as well. and it can be transformed using this particular relationship. So once we transform, we can clearly see that this region is same, or this distance is same as the one which we had already eliminated. And as we said, we had eliminated either this one or this one. So whichever we have eliminated in the other portion, whichever we have written in there, we still have this L1 distance, and which is becoming L2 distance in the second iteration. Now again look into the next iteration. So the next iteration, once we eliminate one of them, then my new boundary length is going to be L03, which is equivalent to L22, which will be of this value as I had indicated it here. And if we further decompose this Fn minus 2, we can write it as n minus 3 and n minus 4. We'll keep it here. And in this, again, if we find out the L2 and L1, we can clearly see that the L2 represents this component and L1 represents this component. So this is my L2 and L1, and using this transformation, this equation, we can reform the L2 in the third iteration as this way as well, and L1 as this way as well. Now looking into the 2 points which we got now, this L2 and L1 in the third iteration, we can clearly see that this particular point is equivalent to this point, which means we already had calculated the point and its function value in the previous iteration. If we retain it, we just need to do it once for this point. So in any iteration, whenever we are calculating the L2 and L1, we can generically represent it as in this format, and the L1 in this format. One thing you need to know in this case is the n, which is the highest order of the series required in the Fibonacci number series. So Fn representing the Fibonacci number which you need to use to start with this particular search method. So with this basic understanding, let us look into the algorithm. Like the previous algorithm, for the lower and the upper bound, we first of all identify the desired number of function we want to evaluate in the process. So as I said, that we need to know the Fibonacci number with which we want to start. So for this reason, if you see that in each iteration we are evaluating at least one function value, and in the first iteration we are evaluating two function values. So we can say that the total number of Fibonacci series we need is going to be one more than the function value we are going to evaluate. So the n is going to be m plus 1. Now when we do this, we also need to understand another component which will be coming towards the end of the algorithm, and we also need to set the counter or the iteration as 1. Then we compute the 2 points, which is the L2i and L1i, and set the first point x1 as a plus L1i and x2 as a plus L2i. Once we set this, we are going to find out the function values at x1 and x2, particularly if it is a higher order of iteration. One of them we are going to evaluate, particularly the one which was not evaluated in the previous iteration. If it is the first iteration, we have to evaluate both. And then we are going to use the region elimination method to eliminate one of the region and set the new boundary accordingly. And as we said that, we increase our counter, the iteration number, by 1, and then check if we had reached the intended number of function we want to evaluate. If it has reached, then we can easily terminate the process and report the interval as A and B. If not, we need to go back to step 2 and repeat the process. And as we repeat the process, we have to keep on checking whether we have reached the number of iterations or number of function values we want to evaluate. As we are evaluating the functions to know whether we have reached the intended number of functions or not, we have to understand the Fibonacci series. So the Fibonacci series starts with 1, the next number is also 1, the third number is 2, the fourth number is 3, and so forth. So if we are evaluating various function values at different points, we'll reach the point which represents 1 by the highest Fibonacci number which we had chosen. Now once we reach this, the next point is also going to be 1 by Fn, which indicates that if you are drawing the function in certain way, and this was my last boundary, the distance from this point to the next point, which is going to be a fraction of the overall initial boundary represented by 1 by Fn, this is fraction of the initial boundary L0. So this point is going to be same if we take the last two Fibonacci number, which means if I am approaching from this side, this is the distance. If I am approaching from this side, this is also going to be the same amount of distance, which means the actual distance between these two is going to be 2 by Fn times my initial distance of the lower and the upper boundary. So the accuracy we can reach in this method is going to be the 2 times of the last distance which we are getting, 2 times of the L2n, which is going to be 2 times of F0 by Fn times my initial distance between the lower and the upper boundary, and F0 is this. If we say this as an F0, then it is going to be 2 by Fn times the boundary. So for this purpose, we have to be careful in which number we want to start, and this is going to dictate the accuracy. If it is dictating the accuracy, solving this problem, we'll find out what is the number we are starting with in the Fibonacci series. From there, we can look into the number of points we need to find out the function values, and that can be equated with the desired number of function evaluations, and then we can estimate what my n value is going to be. It is going to be far more clear when we look into the example. So for the example, we are choosing the same function which we used in the previous interval halving method. Is the minimization of this particular function within the interval of 0 and 3 with an precision 0.2. Now the initial interval distance is going to be b minus a, which is going to be 3, and as I said, the interval which we are looking into is going to be 2 times of the last distance, and we have indicated that as 0.2. Now if we want to calculate the, or if we want to find out the expected number or expected Fibonacci number, we can use the formula where we said 2 times 1 by Fn into b minus a is equal to the accuracy level. So Fn is equal to 2 times the distance between the upper bound and lower bound divided by the accuracy level. So once we fit this in this particular problem, we are seeing that it is going to be 2 times 3 divided by 0.2, which is going to give us the 30. Now if you look into the Fibonacci series, there is no number 30. The closest number which is higher than that is going to be 34. So we have to choose Fn as 34 and start our process in order to achieve the accuracy level of 0.2. Now with this, let us see the solution. So in the solution, when we are looking into, we are looking into the function, objective function, which is here, the interval 0 and 3, accuracy 0.2, and we are starting with the number 34. So we know the initial boundary, which is 0 and 3. Then we calculate the two Fibonacci numbers, which in this case is going to be 34 is equal to 24 plus 13. Let us first look into the Fibonacci series up to 34. It is going to be 1, 1, 2, 3, 5, 8, 13, 21 and 34. So 34, we are representing it as 24 plus 13. So the fraction L2 and L1 is going to be 24 by 34 and 13 by 34. Initial distance between the upper and lower bound is 3. Here is also 3. So these two distance is going to yield me the 2 points, which is 1.147 and 1.853. Now if we evaluate the function at these 2 points, for the first point we see that our objective function value is negative 30.502 and the second point is negative 49.025. Now we can see that the objective function value is lesser at the point x2 compared to the point x1. So if we are looking into the objective function value at the second point, if you have 2 points, you know that the objective function value is lesser here, we can say that my minimum point is either going to lie here or it may lie here. It may have only these two conditions in case of unimodal function. So if we have this condition, then we can eliminate any of the region which is on the left hand side of this point. So what we are saying, my lower boundary is going to move to this new point, and that is what exactly is happening. My lower boundary now is going to be 1.147, which is x1. The upper boundary we are unable to decide, and hence it is going to retain the same. At this point, when we are looking into the precision, we can clearly see it is higher than the precision which we intend to achieve, so we need to go to the next iteration. In the next iteration, we know our lower boundary is this, the upper boundary is this. Then the next iteration, we are looking into the distance of this, because this has been already eliminated. 34 is equal to 21 plus 13, so this is 21 by 34. So 21 can be represented as the summation of 13 plus 8. So the next point is going to be 13 by 34 times 3 and 8 by 34 times 3 from the new boundary, the lower boundary and the upper boundary. So if we try to calculate, or if we estimate those 2 points from the revised boundary, we'll get those 2 points as 1.853 and 2.29. At these 2 points, if we see, this particular point is the same point which we had here as x2, hence we do not need to evaluate the function value at that particular point. We can just retain that. We need to evaluate the function value at this new point which we are evaluating, and then we are realizing that the function value at this new point is lesser than the objective function value at the point which we had earlier, or which is on the left hand side. Now again, if we look into this and in a graphical format, so we have the boundary here, and we are seeing that this is my x2 and somewhere here is my x1. So the function value is reducing in this side, so we can reasonably say that the region is never going to lie on the right hand side of this particular point. So we can move our upper boundary to this new point, which we are doing it here, and we are retaining the other boundary. At this point again, if we are looking into the interval, which is 1.147, which happens to be higher than the bound accuracy we want to achieve, hence we move to the next iteration. We set the boundary, and then the new point where we have already eliminated this portion is going to be represented by this portion, which again can be represented by 13 is equal to 8 plus 5, which can be represented by 8 by 34 times 3 and 5 by 34 times 3. So once we find the value of these two fractions, and based on these two fractions, if we find out the points, we can find out that in the revised boundary these points are going to be 1.588 and 1.853. In these 2 points, we'll find that 1.853 is the same point which we are retaining from the previous iteration, so we can retain the same function value, and at the new point the function value is this. And when we compare these two function value, it is clear that we can eliminate any point which is prior to the x1. So we can shift the lower boundary to this new x1. That is what we are doing it here. And after shifting the revised boundary, if we see the accuracy, still it is not matching our intended accuracy. We move to the next iteration, and in the next iteration it is going to be this fraction. So 8, we can write it as 5 plus 3. So the fractions are going to be 5 by 34 times 3 and 3 by 34 times 3. So again, if we look into the point based on these two fractions, in the revised boundary we'll find 0.1 and 0.2, and this 0.1 is actually the same point which we had in the previous iteration. So we are retaining the function value and we estimate the new function value. Now we'll find out that the function value at the new point is better than the function value of the previous point which we had, and previous point happened to be on the left hand side of the new point. So any point on the left hand side of this older point we can eliminate. So we can move our lower boundary to this new point, which is what we are doing. Again, we look into the precision, it is indicating that we still need to do another iteration. So in this case the retained fraction is 5 by 34 times 3. This one, if we look into, 5 can be written as 3 plus 2. So the fractions which we are looking into is 3 by 34 times 3 and 2 by 34 times 3. Now if we find a point based on these two fractions from the revised boundary, we'll find the points are going to be 2.029 and 2.118, and 2.029 is the point which we can retain it from the previous iteration. So we are using the same function value and the new function value is going to be this. So the point which we obtain as a new point has the function value not as good as the one which we retained. So any point on the right hand side of this new point can be eliminated, hence the upper boundary is revised to this new point. And after revision, once we look into the precision, it is still higher than the precision which we want, hence we are moving to the next iteration. And as we move to the next iteration, now we have the fraction which is written at this level. So this level we are looking into the two numbers which is 2 plus 1. So the next level fractions are going to be this and this. So once we find the points for these two fractions from the revised boundary, we can get this point and this one. It is clear that this is the same point which we had in the previous iteration. So we can retain the function value of that one and recalculate the function value for the new point. Once we do that, we find that the new point function value is not as good as the retained point. So any point on the left of this new point can be eliminated. So we are moving our lower boundary to this new point, and based on our revised boundary, if we see the accuracy, it is within the accuracy we intend to achieve. So we are terminating, and once we terminate, we can say that our optimum point is going to lie within this boundary. So that is what is being reported. we can always choose the middle point of this boundary of our intended result. We can say that our optimum point is expected to be very close to this, or roughly it is going to be 2.029, and the objective function value is going to be 49.956. Now if we want to evaluate the number of functions we have estimated or evaluated in each iteration, we can clearly see that in the first iteration we have done 2. In the second, we retained 1 point from the previous, so we did 1 new. In the third, we did 1 more. In the fourth, we did 1 more. In the fifth, 1 more. And in the sixth, 1 more. So total 2 plus 1 plus 1 plus 1 plus 1 and plus 1, it's going to be 7 function evaluations which we needed in this to achieve the intended accuracy. And if you recall from the interval halving method, in order to achieve the same level of accuracy, we were required to evaluate 9 number of functions. So by using the Fibonacci series, we could reduce the 2 functions, and this could be quite huge if we have a very complex function and we need very precise result out of it. So now let us move into the graphical representation of the solution. In the graphical representation of the solution, you can clearly see the function. When we started, our lower boundary is 0 and the higher boundary is 3. Then as per the Fibonacci series, we chose 2 points. One is 1.147, which is going to be here, and the second point was 1.853, which is going to be here. So once we look into the objective function values of these 2 points, we can clearly see that the objective function value is reducing in this direction from this point. So we can logically say that my optimum solution is not going to lie in this region. Hence I can move my boundary, the lower boundary, to here. So this was my upper boundary initial. So we are moving our lower boundary to this new location, and within this region, once we try to optimize using the Fibonacci series, we obtain 2 different points. One is this 1.853 and the next point is 2.294, which is here. So we retained 1 point and the other new point, and we can see this objective function at the new point is higher than the objective function at the point which we retained. Hence logically we can say the optimum solution is not going to lie on the right hand side of this new point. So we are moving our upper bound to this new point, which is going to be here, and within the revised boundary, again if we use the Fibonacci series and try to find out the 2 points for evaluation, we'll find that one point is 1.588, which is here, and the second point is the one which we are returning from the previous iteration, which is 1.853. And when we compare the objective function values at these 2 points, we can clearly see that the function value is reducing as we move from the left to right. So we can logically eliminate this region and move our lower boundary to the new point here. Then in the next iteration, when we use the Fibonacci series, the next level of the Fibonacci series, and find out the 2 points, we obtain the point as 1.853, which is from the previous iteration, and the new point as 2.029, which is here. And when we compare the function value, we can see that the new point is better in terms of the objective function value, and hence we can eliminate the region here and move our lower boundary to this point. Now in the revised boundary or revised interval, if we use the next level of Fibonacci series numbers and find out the fractions, we can clearly see the 2 points which we obtained are 2.029 and 2.118, which is this. And when we compare the objective function value, we can see that the objective function value at the new point is higher than the point which we retained, so we can eliminate this region and move our upper boundary to the new point which we obtained in this iteration and revise the boundary. Based on the revised boundary, if we look into the next iteration with the help of the next level of Fibonacci series numbers, we find two numbers, which is 1.941, which is here, and the point which we retained from the previous iteration. And after comparing, we can see that the new point has a objective function value which is higher than the objective function value of the older point at 2.029. Hence, logically, we are eliminating the region on the left hand side of the new point and moving our lower boundary to this new point. And at this point, when we evaluated the accuracy, we found out it is within the accuracy we want to achieve. Hence, we are stopping the process and reporting this as the boundary, which is 1.941 and 2.118. So 2.118, which is here. So this is the boundary within which my optimum solution is going to lie, and we also indicated the optimum solution. So this is the graphical representation, and if you see the number of function evaluated is going to be 7. So if we just count the number 1, 2, 3, these are not in order, just we are counting the number 5, 6 and 7. So as I had indicated, we need to evaluate 7 objective functions in order to reach the accuracy level we want. In the previous case, we had to evaluate 9 such function or objective function values before we could reach the same accuracy level. So in today's lecture, we learned about the region elimination method. We discussed 2 different region elimination methods. One is related to the interval halving method, and the second one was related to the Fibonacci search method. We have also shown you that in the interval halving method, we need more number of function evaluations compared to the Fibonacci search method. However, one thing you have to understand, in the Fibonacci search method, we have to calculate the Fibonacci number and the fractions at each iteration. So that may pose additional computational burden in the process. Apart from that, we also can reasonably see that in the interval halving method, we could eliminate 50% of the region in each iteration. However, when we looked into the Fibonacci search method, we can see that for a very large number, we can on an average eliminate about 38% of the area, which is comparatively less than the interval halving method. However, if you closely look into each iteration, the amount of region eliminated in the Fibonacci search method is not constant. it varies. So if we really want to have a precise control on the region which is being eliminated in each iteration, we can rely on the interval halving method. However, it requires more number of function value evaluations. So with these two methods, we can see that we still need certain methods in certain cases if we have constraints with the number of objective function we want to evaluate, or we want to have precision in each iteration to the amount of the region which is being eliminated. So we'll look into those aspects in our next class, in the next discussion, where we'll be discussing about another two region elimination methods. So till then, thank you and see you in the next class.